And if you have any questions or requests, my email is pretty easy. It's merchmgr@sbau.org. And I also, on behalf of the secretary, want to remind members that you have members' name tags over there, and especially to let me know if I not spelled the name right or put too many M's in your name or whatever. And that's it.
Sales today, huh? No? Oh.
For members, if you have your holiday party funds, I'll take them quickly after the meeting, after the talk. So if you have your funds tonight, members, then I'll gladly take your money.
The day of the Christmas dinner is December 11th. Okay, good. Yeah. It's going to be a great time getting you to want to come. So we're going to move right along, and Chuck is going to come up and give a rundown of outreach for November.
Okay. Schools have really ramped up. We've already done 2 this week. And tomorrow night is the second Saturday Star Party here at the museum from 7 to 10, or 7 to 10. And then on the Monday the 10th, we have Coastline Academy in Goleta, which is right at Fairview and Cathedral Oaks. And then on the 13th, we have Peabody School. And on the 15th, on Saturday, we have Midland Schools, where it's up nice and dark by the former Gloved Ones Ranch. And then on the 18th, Goleta Valley Junior High School. On the 20th, it's Hope School. On the 21st, third Friday of every month, it's Westmont College. Then on the Saturday the 22nd, we have Cub Scout Pack 36, I think it is, at Cienegita's, across from the church up there that has a multi-level parking structure across the street from it to the west. And we're going to be up in the top of that parking lot, so that should be fairly dark. And then on the 28th, for AU members who have had the background checks and everything that are registered outreachers, we have an event at Hollister Ranch at Toledo Beach for people and families in Hollister Ranch. And then, of course, like Pat said, we have our holiday party coming up in December. And there's lots of propaganda over by the door there. There's star maps and moon maps and webpage listings and bookmarks, so feel free to graze on those, and thank you.
Yay. Thank you, Chuck. We also have 2 other events I'd like to point out is that every Monday morning from 11 to 12, we have a video log on YouTube. You can tune into that live or you can look at backlog, they're saved. You don't have to watch it while it's on. But if you want to send us a note with a question, you have to watch it, given your time. And the other thing we do on every Tuesday evening from 7:30 to 9, we have a telescope workshop on Zoom. So if you want to be part of that, send me an email and I'll give you the login for that. We primarily do imaging on that lately. But we used to do a lot of telescope building and mirror grinding. That's when we met together in person before COVID. So now, as Chuck mentioned, we have or as Pat mentioned, we have a Christmas dinner coming up, an event planned by our event planner, Diane, who's now going to give us a little talk about that.
Thank you, Jerry. First of all, I wanted to say that we had a really fun event at Kachuma Lake 2 weekends ago. It was really fun. The weather was good. I think it was a little cloudy Saturday night, but there's a little thank you that someone wrote up that attended, that they said the food that Tessa and Chuck and the pancakes and stuff was fantastic. So thanks to everyone for going. The potluck was really fun. We had the main course catered by the Country Meat Market, and so the food was really delicious. A lot of nice desserts were brought in. And you can see some of the pictures on the left there, the group of folks that are enjoying the food. And then The tri-tip was actually, it wasn't cut, so we had to actually cut it at the event, which actually made it more juicy. So it actually worked out for that. And we also started at 4 o'clock instead of 5, which actually made it kind of nice because the people that don't want to stay for the camping could drive back to Santa Barbara when there's some light still left. So it worked out really well. So then we're going to get to the year-end holiday party, which is going to be at the Hilton Garden Inn, and that's at Hollister and Stork. And it's going to be in the main ballroom, the El Capitan Ballroom. And we actually did a walkthrough of the facility before we went ahead and booked it. And it's a really nice space. It's going to be much larger than last year. And we'll also have, in this picture over here, you can see that's the actual room. Now, that screen is very large, so we should be able to get a good slideshow from Tom on this screen. And then here's a picture of one of the appetizer boards. It's fantastic. I'm sure you'll find something that you like on the board. And then this is just a picture of the bar. We're going to have like our own bar area. It's a no-host bar, though, by the way. And then just outside the bar there's a little patio that has like a fire pit. So you can get there early, grab a beverage, socialize, and have a great time. Now these events are for members and their guests. So if you're not a member, please feel free to join. It's $20, which is reasonable. So the timeline of activities is listed in the flyer that you received. I won't go over it, but it starts at 5, so it's important that you try to get there on time. And there's going to be a white elephant gift exchange, which is always really fun. And all of the gifts last year were really great. They were, had the astronomy feel to them, and it worked out really well. So $45, and the money goes to Pat, the treasurer, if you plan to pay tonight. But we'd love to have you all there. Thank you.
Thank you, Diane. First time running to a schedule here. I see we're doing all right. We're ahead of schedule. Is there someone that I've forgotten? Tom Cotton.
Just want to mention, we do have some telescopes available. And on the right, you can see Gail Massey. He's 89 years old. He's giving up an 8-inch and a 10-inch Dobsonian, Newtonian reflector telescopes on a very nice base. And he also has an equatorial platform that actually can rotate the telescopes to track the night sky. A couple $1,000s for one of those white aluminum fixture there at the bottom. But we have a 5-inch and an 8-inch and a 12-inch telescopes available. Yeah, a lot of people are getting little $500 sea stars, but they cannot zoom in on the planets like Saturn and Jupiter. So you really got to buy one of these bigger telescopes to get the whole view. So contact us and equipment at SBAU, and I might look at the email or just somehow get a hold of us. And if you're looking to get a hold of the telescope, and we'll talk to you about what you might be able to handle. Jerry?
It looks like you have some eyepieces at the bottom there.
Eyepieces available.
Is there any one type that's there?
What kind?
Is there any one kind?
Well, there's Meade and Celestron.
That's a mix of things.
So yeah, there's different groups. Or some are contained in a box. They have all different types. And some are loose.
Okay.
Older camera things. So
Thank you,
if you're like experimenting, we've got some older things that you can try to get working too. Yeah,
Well,
what
that
else do we
leads
have
us
here?
down now to our vice president.
We can-
Oh, yes, one more thing involving the vice president. It's his job to put together a ballot for who wants to be a club officer. So if you're hankering to get all the perks of being an officer, put your name in with the man here.
Appreciate it.
Okay.
The
Ron.
old slate. Thank you, Mr. President. Let's give Jerry Wilson a hand. All these years. We're going to vote him in again next month. We have a half hour and we're down to 15 minutes. We've always had to rush this part. get to the speaker. Amazing, we have 9 o'clock as the deadline and yet an extra half hour just to do the meeting. And some of us in this incredible club, ladies and gentlemen, like to know, I do, who is here. So I'm gonna do my little show of hands. First timers only, raise your hand if this is the first time you've ever been, oh. You're the ones we're gonna focus on and buy the beer for. Incidentally, I just bought my ticket for the meal tonight, because I get my money's worth at those things for $45. I kinda go to the hors d'oeuvres table at the beginning and put my jaw down at the edge of the table and sort of walk across. It's gonna be a good show. Who has been here before, but is not in the club? Okay, something we did was right. Give these people a hand. That first group, we want you to become this group now, the second group. Now, members only, SBAU. Oh my God, we're dominating. Look at that. And it's going to be important next month. December is always a special month for the Santa Barbara Astronomical Unit, because we not only have the election, which will be done by a show of hands, by members only. It's just $20 a year for crying out loud. I'm drinking Harry's for that. You got a fun family of people that are going to be new friends. Anyway, we're possibly going to be short of secretary, because of the election, Tessa, the beloved Tessa, who I think deserves a great round of applause. She helped me get tonight's speaker. She told me, you ought to get this guy that is speaking before the Mount Wilson fundraiser. And I said, really? And she said, yeah, Dr. Phil. I'm not ready to introduce you just yet, doctor, but I got a couple other things to do. I went online and checked that fundraiser out, and they charge $50 and up to get in. And I told her, can't afford this guy. I contacted him anyway. He had just been to our museum with his 2-year-old daughter on his way to the campground in El Cap. And we were holding one of our events that night. He just barely missed it. He'll tell us about it. He's also got guests with him. But I just want to say that next month, please come, please vote. If you want to run for Tessa's job, we could sure use somebody with secretarial skills to take down the minutes of our monthly meetings, which are always staged online on Zoom on the second Saturday of the month. We're doing it tomorrow. Our second Saturday meeting and Star Party happen to be in the same weekend as our first Friday meeting, which is here. We also have, we're very proud of this, and it's, since it's my job as Vice President to come up with all the speakers, we get 2 people or 3, depending, there's only an hour to talk, that are among our members. Members only, I call it the in-house members only speeches, and we got 2 good ones. Is Matt here? Matt, are you poking? That's the man. He just said hi to me. We're not drinking, buddy. Meet your counterpart. Shake hands with David Grossman. These are our 2 speakers for next year. Let's give them a hand. Matt came to me last month or a month earlier. Who else is here? We don't have a 3rd speaker. Jerry?
No, I just wanted you to make a comment that you made secretary sound too fearsome. Taking the notes. Zoom will take the notes for you.
We're just gonna let the Zoom be the minutes?
If you want. It depends on the personality of the secretary.
Well, I thought we were gonna discuss that, but if that's the way it is, you got it. I'm sure we might get somebody. You got a month to get in touch with me, even on that night. We might have it solved, I don't know, I can't give any names or any possibilities, but we'll find out. In any event, David Grossman's gonna talk about one of his articles that he wrote for Astronomy Magazine. He's done 5. And one, he's gonna be able to give us, in his presentation, what he couldn't give the readers of astronomy. The name of his article was Sonification, taking data from space and turning it into sounds or music. It can be done. If you tell me those people reading astronomy could hear any of those sounds, we will be able to hear. And then Matt Hall has been in the club since the 80s. That's almost 50 years, young man. Can you believe that? He was a president, and he's also building a scope, right?
Astro camera with an old
a Korean War spy.
4x5 film.
We all have one of those. So that'll be in this fall, and it'll be same the earlier times, and it's next month. In the new year, I gotta tell you, we've got two, I'll do the first 3 months. We've got two from UCSB. One is a lady professor of astronomy, and the other is an up-and-coming grad student who was recommended to me by Omer Blyas, one of the retired professors of astronomy out there that we've had speak to us before. I tried to get him back, and he said, no, I'm gone, but I want to recommend this young man, and he'll be here. And then our third one will be JPL expert on volcanism, science from Jet Propulsion Laboratory. That's the first 3 months of the coming year. So let's get right to it. Oh, let me repeat, we're on YouTube, as the president is starting to mention these days, on Monday mornings. We're about to wrap up our 5th year. It's called the SBAU Astro Hour. I won't say a lot because it's up there. Wrong picture. The picture is, I think, the Tuesday night meeting of all you astronomy buffs. There's 6 of us. I think only 3 of us in the room, maybe 4. Well, anyway, join us on Monday mornings for that. Okay, as I told you, Dan said, I love your museum. My family loves it. He's brought several of his guests, fellow professors or scientists. Some of them are teachers class. They're all involved, I think, in some way or another with SphereX. And they're sitting down here in the front row. You gentlemen want to raise your hands just so we know who to talk to later on? There you go. Okay. One of them has already agreed to be a speaker for me in the middle of summer. And I'll let you find out. He's connected to another telescope at the South Pole called BICEP. And I can try to imagine what the southern sky from Antarctica looks like. Anyway, you can find out from him and you'll see him later on. Dr. Phil, Caltech, SphereX, NASA's new Cosmos mapping machine. He's an instrument scientist, holds a research science position at Caltech Laboratory for Observational Cosmology down in Pasadena, as well as an affiliate position of NASA's JPL, obtaining his PhD in physics in 2011 from the University of Pennsylvania, where the man developed a receiver based on superconducting detectors for the Green Bank telescope. I think he'll tell us about that. For his dissertation, he used this novel camera to study shock waves in the superheated plasma of merging clusters of galaxies. He's our own Dr. Phil. He's also developed a fielded NASA sounding rocket mission, including the Cyber series that were designed to study the extragalactic background light. Ladies and gentlemen, from Caltech, Dr. Philip Korngut.
Thanks so much, Ronnie. And thanks everyone for coming out. As Ronnie mentioned, it was not hard to twist my arm to coming here. I'm a big fan of Santa Barbara. This museum is fantastic. I'm particularly fond of the pygmy mammoths because I spend a lot of time out the Channel Islands fishing, and I just think that's the coolest thing. And I love this. I love this museum. So, should I share? We're gonna have to reshare here.
All right.
Okay, let's reshare.
Nice. How many stars in that picture?
We'll get back to that. All right. Well, I'm here to tell you tonight about SphereX, which has been the focus of my career for quite some time now. And I'm really excited to show you what we've been doing, how we put this mission together, and some of the first exciting results that we're coming down from this telescope. So, in the great tradition of NASA missions, SphereX is indeed a tortured acronym. It stands for the Spectrophotometer for the History of the Universe, Epic of Reionization, and ICE's It's a mouthful, but I promise you that is actually quite descriptive of what we're doing. I hope by the end of this talk you'll understand what that means. SphereX is an explorer mission, a mid-X class mission, and this is a series of missions at NASA that have done great science. It's the largest scale mission you can do as a PI-led mission, so principal investigator-led, which is, they're really physics experiments as opposed to flagships like what you might be used to for Hubble and James Webb and things like that. So it's a targeted physics experiment.
Phil, can I ask you to turn your video on so that people can see you at home?
Okay, let's see here.
Right, the lower left.
Can we have the lights down?
Actually, we need some of that for recording, but I don't know if we can cut half the lights or not.
Do the back?
Yeah, that'd be great.
That'd be great. Yeah, the front would be great to turn down here if we can.
Yeah. We want to have a light on you though, so we can see you.
Okay. In the spotlight.
There we go, that's the
This is where I
back.
left
There we
it
go.
off.
Okay, good, good,
I have my video. No.
good.
All right, we'll make it work, right? All right, here we go. As I was saying, yes, so we're an Explorer program mission, and you know, these opportunities really come around about once or twice per decade. So we really like to tackle big questions. So for SphereX, we designed the mission to get at three of these more fundamental questions. What are the conditions for life outside the solar system? How did galaxies begin? And how did the universe begin? So very grand questions indeed. But we've really optimized it to get at some really interesting information, started to tackle these questions that have kind of resided in philosophy or most of humanity's history. I'm going to take you through these. Let's start at the biggest scale, really the biggest scale imaginable, right? How did the universe begin? Well, here's a cartoon of kind of the history of the universe as we understand it. In this diagram, the x-axis here is time, right? So from going back 13.7 billion years to the Big Bang. And the diameter of the cone, as we move out, represents the scale factor of the universe, the size of the universe as it's expanded out. I'm sure I heard you had Alex Filipenko here last month. I'm sure he was talking about the very right here in the accelerated expansion. But with SphereX, we're trying to get at that very, very earliest times. So we know from studies of the microwave background, that's this relic signal from about 400,000 years after the Big Bang, some pretty profound things about the universe. We've learned a lot about the energy content, the makeup of the universe, the dark energy, dark matter, baryonic components, and it has been an amazing wealth of information. But it also has some results that posit more questions. These observations, which are absolutely just beyond a shadow of doubt at this point, is that the universe is uniform on the largest spatial scales, and its geometry is spatially flat. These are actually two very profound observations and hard to explain. And the best method we have right now of explaining those is a theory called inflation. Now, this was cooked up to solve these problems, called the horizon problem, around the early 1980s. This is one of the early papers from Alan Guth, and I love this plot because it has 100 orders of magnitude on both axes. Right? That is an unfathomable scale to put in there. In this plot, the cosmic microwave background is like all the way, it's like here. You can see that. Oh, you can't see my mouse, but it's all the way to the right here, and you can see that dip. The idea of inflation is that the universe underwent a period of extremely rapid exponential expansion, just tiny fractions of a second after the Big Bang. 10 to the minus 32 seconds after the Big Bang we're talking about. Today is only 10 to the 17 seconds after the Big Bang. So it's an unfathomably small amount of time. So how can we possibly access information this far back? Well, if we look at the universe today, and this is actually real data from a Pathfinder ground-based instrument called DESI. Each dot in this image is a galaxy. Right? Each point is a galaxy. And what you'll notice is that they are not randomly distributed. Right? They're clumped together, and they form this lattice we call the cosmic web. Right? And the origin of that structure is actually quite profound. In the Big Bang, when the entire universe was smaller than the scale of an atom, it's governed by quantum mechanics, right? And in quantum mechanics, you have tiny little fluctuations, little overdensities and underdensities that are governed by quantum mechanics. And as the universe expands, through inflation and later on cooling and condensing, those little overdensities and underdensities, those turn into that large-scale structure that we were just looking at. And galaxies and all the star formation and everything we see actually forms in the peaks of those density fields, so the little overdensity. So if we look at the universe today, it's tracing that structure. So the idea is if we look at the universe today and do precise statistics on that density field, we can actually learn about those very first instants right after the Big Bang. So taking a different look at this timeline, and now moving on to our next science theme about the history of galaxy formation and evolution. We study something called the extragalactic background light. And that's really just a fancy term for getting at the integrated light emission history of the universe, right? Around, 500 million years after the Big Bang, we have this epoch of reionization. This is the time when the first stars begin to ignite out of the primordial hydrogen and helium and light up. Those are really bright in the ultraviolet, but it's really far away in redshift, so when we observe those today, it comes into the Earth.
Yeah, maybe you could unmute.
If I unmute here, I think that'll, is this microphone not feeding into the web?
No, so if you, yes, better unmute.
Okay, I'm worried about the
Didn't notice that.
feedback action here. Let's give it a whirl. Speaker is off here. Can you hear me online? Is that better online? You should be able
Yeah,
to hear through my laptop.
it'll be better, I'm sure.
Okay.
That's good,
Okay.
that's good.
All right.
No wonder.
Check the chat and see what's
I'm gonna keep moving here. All right, I think we're good. We should be good here. Okay, so I was saying the extragalactic background light. So this is really a signal, the aggregate signal. So we have that earliest signals from the epoch of reionization, but all the way to modern day. We have the diffuse light from stars that have been flung out to the outskirts of the galaxy. We call that intrahalo light. Those are emitting in the infrared today. So what we measure is the integral of all of this light formation, the total light production. And this contains a wealth of information. So how do we get at this? Well, we use a technique called intensity mapping. And if we look at a matter field, like we were just discussing, and the galaxies, those just live in the bumps, as I mentioned earlier. So if you're just studying the galaxies, you're just studying a field that looks like this. With intensity mapping, we actually study all the light that populates throughout that cosmic web. And we do that through statistical studies using measures like the power spectrum, and we do that with SphereX by separating out this light field into its constituent wavelengths or colors. Of course, we're talking about the infrared, so your eyes won't work there, but by separating out this light field into its constituent wavelengths and cross-correlating between them, we're able to disentangle the light production and where it came throughout the evolution of galaxies and the history of the universe. Closer to home, we're interested at getting at the conditions for life to form outside of our solar system. And for as life as we know it, at least on Earth, that means water, right? We need water to have life. And the vast majority of water in the universe is not in liquid form, it is in ice form. So with SphereX, what we do is to study many, many lines of sight in our own galaxy with background illuminating stars. As the light transverses through all sorts of intervening mediums, they imprint spectral features, which at a special wavelength, there are 3 microns. Water ice is black, basically. It's not see-through, it is black. So when it imprints, you'll remove that color from your spectrum, and you can use that to study water in the evolution of planetary formation. And really, with SphereX, at its core, what we're doing is to map the entire sky spectroscopically. This is a new technique. There have been many all-sky surveys in the past. These are all continuum or broadband imaging. And as the adage goes, a picture is worth 1,000 words, but we like to say a spectrum is worth 1,000 pictures. You can separate out that data and you learn so much more. Here's some statistics I'm not going to go through, but truly anything that you are interested in getting spectroscopy on, we will have a statistically significant portion of it, and this is a really exciting thing. I think that the most exciting things that will come out of SphereX is not the things that we built it for. This is just a tremendous data set, and it will all go out to the community to be mined for whatever you're interested in studying. So let's switch and talk about the actual payload here. Here's an image of SphereX, but it's cut away here. On the bottom, this is the spacecraft bus. We call it a bus. It really drives us around like a bus up there. This is what does all the communication with the grounds. It points us around. It navigates, keeps us our power. And then the canonical feature of SphereX is our martini glass shaped cones here. These are called photon shields. And their job is to get us down to ridiculously cold temperatures. For an infrared telescope, it is absolutely quintessential that the emission that comes from all hot objects get removed, including our own telescope. We don't want to be blinded by the light that's actually glowing off our telescope in the wavelengths that we operate at. And the photon shields and the V-groove radiators are passively cooling, so we can cool down to this temperature without using any refrigerators or cryogenics at all. It uses the heat sink of the dark sky itself to radiate out our power and cool down. At the core, SphereX is a wide field 3-mirror telescope. This type of telescope is a 3-mirror anastigmat. It is not obstructive, not like if you have a Cassegrainian or a Newtonian telescope or Dobsonian, whatever. Those typically have secondary mirrors which obscure the aperture, right? You'll have it in the middle, and that creates diffraction spikes. Even in the planetarium, I was looking at some of those, the renderings they have those plus signs. Those come from your spiders that hold your secondary. With a 3-mirror anastigmat, you're off axis and an unobscured aperture, so we don't have that. We also use what's called a dichroic beam splitter. So you can see there where the blue and the green rate paths diverge. That optic behaves as a window at some wavelengths and a mirror at others. So we're able to put 2 focal planes that simultaneously image the sky, each of which have 3 detectors, and they sit behind a set of linear variable filters. These are the core of SphereX's spectroscopy. Our wavelength range goes from 0.75 microns up to 5 microns, and it has a range of resolving powers of spectroscopy. How small of a wavelength color can we measure? So the LVFs, they really behave like a bandpass filter, like you might have a H-alpha filter or RGB filters that you use in your telescopes. This is the same concept, except that the wavelength band varies as a function of position. So wherever an object lands on your focal plane, you measure it at a different wavelength. And we use this, and we have designed our survey to build up a spectrum of every single point on the sky. So we operate from low Earth orbit. We go around on a sun-synchronous polar orbit about 650 kilometers. We basically live on that terminator line. We go around and we must avoid the sun. That was the yellow plane you saw. And the Earth is the green zone. We can't tip over too far, or we'll warm up from the Earth shine below us. So we move along, pointing the linear variable filter at a series of positions, so we can measure a spot, and then make a little slew, measure another spot, and then once we get close to tracking the edge of our avoidance zone, we make a large step and go to the other end of that zone and keep going. We just do this relentlessly, and as we're going around the Earth and until we fill in everything. And that looks something like this. This is sped up. But it takes us 6 months to cover the entire sky, right? We're in that sun-synchronous orbit, so we go around the Earth, and we were just following that terminator line, and it takes 6 months to build up a complete spectrum. Our baseline mission is to do this 4 times over the course of 2 years, and we're now about 6 months in. It's important with this kind of survey pattern to note, right? We cross at the poles every orbit. That's true all through the year. So what this does is it enables us to have two regions at the poles, which are we call our deep fields, and those are what we use to study the extragalactic background. All right, let's switch to a little bit of a history of SphereX, what it takes to actually get a mission like this selected. We started way back in 2012 formulating this concept. Originally, it was a SphereX, not a MidX. We proposed it, it's a smaller class mission. And that's when we started our concept studies, developing what the ray trace would look like. And by the end of that campaign, SphereX looked like this. And we had submitted our first proposal, what we call our step 1 proposal. At that time, we were one of about 20 mission concepts, of which NASA down selects and chose 3, and we made it there. So that puts us into a phase A, is what's called. NASA gives a small amount of money to develop the concept further, but they do this for 3 missions. So it's kind of a showdown where it all rolls up. We develop a further study. We call that a concept study report, when SphereX look like that. And then you submit that, and then NASA convenes what's called a site visit, where they hire a referee panel of about 35 experts, and they come and they kick the tires and they really try to get into it and make a recommendation to NASA of which mission to select. And we lost when they chose IXPI, which was an X-ray polarimeter over us. But fortuitously, before the selection of the SMEX, there was a call for a MidX round. And so we put in another step 1 as a MidX, which allows for more money. Well, we kind of jammed in there before we heard about SMEX, and then we made it to phase A again as a MidX this time. So we go start the cycle again. We write another concept study report and mature the design further, this time as a MidX. Have another site visit where you defend in front of a panel of referees until there's a final down selection. But at the end of it, this is the stack of proposals that we have written. It's, I don't even know how many thousands of pages, but it takes a long time. And then by February of 2019, we were finally selected for implementation. Here's a picture of our leader, our principal investigator, Jamie Bach, being notified by the selection official at NASA. This was a great celebration and put us into the implementation phase in late 2019. So we all know what happened in late 2019. So as soon as we got selected, COVID came around and we went into lockdown mode. So all of the design phase was done in our own garages. We had electronics engineers setting up shops in their houses. Development like that. We went on to preliminary design review in the pandemic lockdown. This is what SphereX looked like around then. We move on for what we call phase C. Now we're starting to implement, right? We purchase the long lead items, we specify and procure that's holding a linear variable filter that we ended up flying. This also is, I love this picture because it's a great illustration of just how efficient of a spectroscopy linear variable filter is. That's a few grams of sapphire that I'm holding in my hands like that. There's no big dispersion gratings or things like that, no fiber bundles. It's a very mass efficient way to do spectroscopy. We start doing prototypes of the focal planes and lots of testing calibration. We also built the telescope. This is done with our industrial partners that was formerly Ball Aerospace, is now BAES, out in Boulder, Colorado. And here's some pictures of what the optical testing at telescope level looked like. And then we have to bring everything together. And I'm going to spend a little bit more time on this phase because this is really like, the part that took place mostly in our laboratory at Caltech and, my favorite testing. The focal planes, those go through their own suite of tests that we've done at between Caltech and JPL. As I just showed, the telescope went through its own suite of testing out at Ball in Colorado. The thermal system, that's a V-groove radiator. You can see, 6 pictures of me reflected there. That's what dumps all that heat out to deep space. And those all come together into what we call the instrument. Now here, you can see it put all together. It's a telescope mounting, as it will be in flight. We have all of our harnessing, our wiring, everything is staked as it is in flight. So there are 2 absolutely necessary measurements that we had to make on the ground before it gets off. First, you have to make sure it is in focus. You know, you don't have a little knob to go reach for. And everything is stable. You get to set it once on the ground, and it better be right. And you have to measure it on the ground in the environment that it will operate in space at 45 Kelvin. Well, that's minus 350 something Fahrenheit. 348. Calibrating the spectral response of the system. That's another thing we must do on the ground. We have to know which wavelength lands where. So to do this, we came up with a concept of building a cryogenic chamber. We did this with our collaborators at KAZI, which is over in Korea. We worked with the Korean Space Agency to develop this concept, where we had two modes. We could do it in an optical mode, with a giant window that could look out at a collimator in our laboratory to measure focus. And then with a series of integrating spheres, which I'll show later, to do our spectral calibration. We had our kickoff meeting in December of 2019 over in Korea, and we were in Korea when we heard about this weird flu in China. So we ended up developing that chamber completely remotely across the Pacific collaboration, and it showed up at my laboratory in about 2022. Here it is coming into the loading dock of our building. The laboratories in the basement of the Cahill Center for Astrophysics and Astronomy, and the loading dock cannot accommodate to go downstairs. So the building was equipped with what we call a crypt. We remove a section of driveway, and we had to bring in a series of cranes, so we're lowering it down to the basement. It was quite a task. And here's the Korean team coming over after we commissioned it in the laboratory. So we also set up the facility in my lab to do precisely this task. And for that, you need to have an optical testing facility, as well as a clean facility, which is contamination control. You can't have any, beard hairs on your mirror in orbit. So we have to do that in a controlled facility. So this is what it looked like doing that operation. We're coming out of our lab in the calibration facility, and then we can push it in where we get bunny suited up and we can work on the sensitive optics. And this means that when we're doing the calibrations, we don't have to be fully bunny suited. It's a much more reasonable way to go about things, and it worked out quite well. This is what the focus testing looks like in our lab. You can see looking at that massive sapphire window, and it's looking at a series of relay mirrors. Those go to a collimator, right, which is just a telescope used in reverse, essentially. So we can project a source out to infinity and dither it around so we can make measurements of focus. An interesting thing of doing this, of course, in the infrared is that you have to throw away you only keep 1 part in a million of your light. And that's because your laboratory is glowing at a ridiculously bright level, right? It's at 300 Kelvin. Here, as you can see, this is a cold filter that we operated inside the cryostat, and throw away much of that, but it has to preserve wavefront error. It has to throw away 6 orders of magnitude of light and not scramble your wavefront error. So that was quite a challenge. So how does this work? Well, it's the same thing as when you go to the optometrist. The way it works, you look through those things, you look at a fuzzy thing, you say, it's better now when you put a refractive correction in. But in Larry's case, you leave that refractive correction in, right? I'm wearing my refractive correctors right now. We just walk around with them. In the case of SphereX, what we do is we cool down everything to its operating temperature. We scan in and out of collimation. We measure where it is. We know where it should come into focus because we know where infinity is. We calculate the difference and fit a plane, and then we warm everything up. We shim it, and this has to be done to about 20 microns. So, a tenth of a human hair kind of width. And then we lock it down, and it better be in the same place once we get up and to work. We then have to subject it to vibration testing. This is a harrowing task where the thing that you've just built and spent countless, decade of your life, and you put it on this table and shake it to smithereens, and then you have to cool it back down again and make sure the focus didn't shift after being so nasty to it. And then we proceed on to spectral calibration. This is the concept we came up with and built in the composite chamber. This is my favorite photo because it's our most Bond villain-like looking apparatus. What you're looking at there is the Winston cone and a cryogenic integrating sphere. And that is designed such that we can couple in a single wavelength of light and it will uniformly illuminate the aperture. So you're putting your telescope into the business end of that Winston cone, and then it will be coupled in. This is what that looked like in operation. So in that photograph you can see on that table, that's where we generate a single collimated beam of monochromatic light, and we steer it into this apparatus, and this is what the measurements look like. So you can see that stripe moving along. Even though the entire field of view is illuminated uniformly, it only lets through a stripe. That's the magic of the LVF, right? It only lets through a stripe at the position which corresponds to the wavelength that you've injected. So we scan this across the entire way. This took us, a 4 months or so just stepping through, and we're able to build up this spectral calibration. This is what the real photons shields look like after we put them together at JPL. Truly remarkable pieces of reflecting radiators. And then after we're done with the payload, what we call the payload testing, we ship and we integrate to our commercial partners out in Boulder, Colorado for spacecraft integration. At that level, we put everything together again and subject it to more cryogenic testing. Here it is in the Titan chamber. Remember, this is a 2-meter tall apparatus, and it looks like it's tiny in that. That whole thing is a cryostat, right? So the whole thing cools down, not quite to 45 Kelvin, but to 100 Kelvin or so. And then here we subject it to acoustics testing. Those are speakers. That is a stack of rock and roll speakers because it has to withstand the sound of the rocket launch, which is unbelievably loud, as I'm sure you all know living in Santa Barbara County. So at this point, it's nice to just take a step back, right? In 2012, when we started formulating this concept, this is what SphereX looked like. This is what I looked like. I was a 28-year-old young postdoc, bright-eyed and bushy-tailed, just out of grad school. That was the year of Obama versus Romney. That was the year that Facebook had its IPO, which just seems like a million years ago. And then fast forward to 2025, and that's what SphereX looks like. And this is what we looked like right before shipping. It was really something special when you actually look at this thing that has existed in our minds for so long, and we actually built it. And now let's get it off the planet, right? That's where we moved. And we did that here, right? There's us at that red dot, and just in your backyard is the Vandenberg Space Force Base. It's a remarkable chunk of California coastline. It's enormous. It spans all the way there. And we launched from Slick 4, Space Launch Complex 4, from the Falcon 9 pointing south. This is great for polar orbits because there's nothing south of us until you hit Antarctica. This is what it looked like as we arrived at Vandenberg. That's our transportation, and you can see we had to tow along our environmental conditioning. You have to keep the right humidity or the right temperature, crossing the Rocky Mountains from Boulder. And this is January 2025, so what else was going on in January 2025? That's what JPL was like that week, literally while we were shipping. So we had plenty of people working that had their houses, they lost their houses, and we made delivery on time. We had to divert the route that we had taken to avoid Southern California, but made it to Vandenberg on time. Integrated, this is us being built up in the stack to come on to the rocket, at which point we got our buddy's Punch installed. So this was the first ride share that NASA has done. And we simultaneously went with the Punch, which is a heliophysics mission to study the sun, going to a very similar orbit. So it was a good bang for your buck with the 2 missions on a single Falcon 9. And this is what it all looked like at encapsulation, coming together in that enormous fairing. The campaign took some time, but we got to the launch pad. It was pretty surreal. It's absolutely stunning out there on the coast at the launch pad. That's myself with our principal investigator Jamie Bach and our project scientist Olivier Doré. And that's what the full stack look like. Remember that picture I just showed of the encapsulation where SphereX looks tiny in this enormous cavern of a fairing, and look at the fairing on the top. That's how big these things are. And here we're going to go for launch. We don't have audio set up, so I guess I can narrate. All right, so 3, 2, 1, rocket away. Here we go. It's launching on the way up. Tremendously exciting. The first stage burns only for a few minutes, but it's enough to get us all the way up there. Then the second stage booster, you can see here, that's the first stage separation. Now it's coming off. The second stage ignition. Now we're well into space and heading south. This you could see from here remarkably. It was a nighttime launch, perfectly dark. It was incredibly unique. And here comes the fairing separation. Opens up, and then there's SphereX out in the environment that it was meant to be. And here we are, about to be separated. This was the control room at Vandenberg, and there it is being separated, lifting off and drifting away. And this image is forever burned into my eyes. Yeah, that's right. It came back down, and we were standing right below it. It's something to watch the thing land. But what's so cool about being in Southern California is not just seeing that amazing video, but also videos that look. This is a friend of mine, some friends of mine at their house in Burbank, watching a SphereX launch, and you could just that's just so crazy to think about it here. I know. I mean, I'm sure the specialist is worn off from you guys here hearing it all the time, but it's so amazing to see, and that's it's reality. You can see it from this is like half a mile from Burbank Airport. And then we proceed into what we call in-orbit checkout. This is in the what we call the EOMOC, another tortured acronym, Earth Orbit Mission Operations Center. This is where we talk to SphereX, and we send up commands, we get our data down, and make sure everything is going. We had to power it on in a tremendous, a very staged and dialed-in fashion. But after about 3 weeks of doing this and doing a cool down of passive cooling and everything, we got to the point where we could finally turn on SphereX and take an exposure. And the first exposures look like this. So we color-coded here to represent which wavelength you're looking at in a single image. Remember, this is a spectral image. It's different than what you're used to looking at in astronomy because each pixel has its own wavelength, right? And remember, we have a dichroic beam splitter. So you're looking at the same chunk of sky twice on the top and on the bottom. And this is 11 degrees across on the top and 3.5 wide. So a few things stand out right off the bat. You can see those really bright stars there, but this is such a large field of view, it's really hard to see what's going on. We can zoom in a little bit, and there you can see, there's a foreground nearby galaxy there, and all sorts of dots, and then we zoom in further, those little dots that are just barely at the signal to noise threshold. Those are the faint distant galaxies we're going to look at. So this is a zoom in of a single exposure. We take 600 exposures a day, and we do that nonstop for 2 years. So that kind of gives you the scale of what kind of survey we're doing here. But there's, of course, one more feature in this image that you're probably thinking, what is that? What is that line? And it's a lot like those spectral calibration images that I was just showing, right? Well, here's another picture that's actually taken before this. This is a photograph of the first time we actually got photons through our detector. And this is with we don't call this first exposure because we were not yet controlling the attitude of the spacecraft. So the spacecraft is just drifting along, and it's 115-second exposure just with the entire universe flowing through. And this photograph made its way around to all the JPL leadership and up to NASA chain, and it was kind of sent around. I was like, look, the scientists are so excited that things working. Well, my hands on my head because I was like, oh my God, what is that spectral line? We did not expect to see that thing going across, right? So what that is metastable helium in our Earth's upper atmosphere. So this was not really studied before because an instrument like this kind of hasn't been in that neighborhood before. There have been spectrometers that study the Earth's atmosphere out there, but they point down, right? So they're getting the whole integral of the atmosphere going all the way down. We are at 650 kilometers in space, right? The International Space Station is at 300 something kilometers, right? So we're up there. There's still an atmosphere up there, and it's glowing. in this particular wavelength, 1083 nanometers. And this was the first community paper come out of SphereX. So that lemonade that was like, oh my God, what is this foreground we're going to do, has already branched out into another realm of science, and this is some of the earliest papers that have come out. That's not from someone on our team. That's someone who just looked at our data and is studying the metastable helium in the lower Earth atmosphere. So where is SphereX now? Well, we're here in November. We started our first survey in May the 1st. So we are almost done with our first 6-month survey of the sky. Each dot here is a target that we set forth to image, and you can see there's just that little stripe there of white that is remained. So you're a very fortunate audience. We're just getting together now, our first all sky spectral images, and happy to share that now with what that's starting to look like. So here's an all sky image. This is a composite image of about 8 wavelengths, right? Of almost every position on the sky. And to show this, we've degraded the resolution of the image by a factor of 10,000 or so, right? Because this is just every pixel. This is the entire sky projected out into mole-wide, like you might look at a map of the Earth projected out. But even in this 8, wavelength image, this is not showing what SphereX is great at, because you just can't collapse these data in the spectroscopy into a single image. It's more convenient to look at it as a movie where we can cut through the data cube. So here we're starting off in the short wavelengths, and you can see the dust lanes going across the galaxy, because the short wavelengths, they're optically thick and it's obscured. And we started going through, you just saw helium pop up there, and now you can see the galactic center. Anyone know what the S you see there is? That's right, it's from our solar system. That's the zodiacal dust cloud. You can see the Magellanic clouds down there too. And we just passed so here we're about to be at PAH. You see those molecular lines light up. PAH is like, you can think about it in barbecue, your tri-tip had PAH in it. And then we're at bracket alpha of hydrogen. There's all sorts of stuff in here we're just starting to begin to unpack. But so this is the full zoomed out version, right? This is everything. Let's take a look at a few zoom-ins of what our data looks like. So here's another just 3 wavelength image at the deep field at our north ecliptic pole. And every dot you see in the background there, that's a galaxy, right? So there's this tremendous light field that you're seeing. The bright things that are multicolored, those are the foreground stars, right? Those are just in our way, in the front. And this is an image containing that extragalactic background light. So our work is now underway, disentangling that. But again, a 3-color image is not the way you look at this. Here's another way of looking at it, which is to stack everything up in a cube. So look at this cut across, and now we're flipping around in our cube. It's like a book, where each page in the book is another wavelength. And you can just see those bright objects form these lines that cut through all the way to the book, because that's all of the information, the spectral information that's contained. And our task is now underway, disentangling all the components that come in from the integrated history all the way back. And the data is looking quite good, and we've already got some pretty aggressive detections in separating this out. So what about closer to home? Well, if we do look at it at a mosaic nearby, this is in the Cygnus region in the galactic plane, and these are 3 wavelengths again, but these are chosen differently. One of the wavelengths, the wavelength that we had chosen to use in green here, is at 3.0 microns. If you remember earlier, 3.0 microns is a very special wavelength because our spectra of some objects will look like this, right, where that has that dip in 3 microns, which is missing light at 3 microns from background illuminating. And that is a telltale signature of water ice. Right? So when you see these dark lines here that appear in green and 3 microns, those are likely contain tons of water ice. So we set out in SphereX to look at a bunch of individual, clean, isolated background sources and look at the intervening absorption. But when we look at these maps, you can just see it with your eyes. We're calling these interstellar glaciers. But so this is the work to separate this out, and exactly how much water is contained is underway, and we have papers being put together now. But it's really remarkable. It just falls out of data. You don't have to do too profound of an analysis when you see those dark lines of 3 microns. You know that water is everywhere. All right, so now moving on, this is not SphereX data. I'm sure some of you will be familiar with what this object is. That's data from the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Right, they found a moving object. That's what this telescope is designed to do. It's designed to find objects that could potentially come into contact with Earth, meteors and comets and the like. But when you look at the motion of this and study its trajectory, it looks something like that. Extremely hyperbolic, right? This is 3I Atlas. It is not from our solar system. It is an interstellar traveler. This is a comet that has been ejected from its own solar system, been traversing through interstellar space, and is just falling into our backyard, coming right now. So if you remember, from our observation strategy, we can only point at certain places at certain times, right? You can't look close to the sun, and you can't look too far away from the Earth. We have this band of regions which is accessible to us. And luckily, that was discovered July. Mid-August, 3I Atlas went into our observation realm, and we were able to get spectrophotometry on it. And here's what I saw. And I nearly fell off my chair when I saw this. So this movie, now each frame of the movie is changing in time as well as in wavelength. Right? So it's a little bit weird, and this is taken over 2 orbits. So you can see the first 4 frames, the stars are kind of moving a little bit, and then they take a step over. That's because we took about 4 images, and then we couldn't get to it again until the next time we came around the Earth an hour and a half later. These are also separated around 4.3 microns. 4.3 microns is a very interesting wavelength because it's where carbon dioxide emits. So when we combine that and stack it, we get an image that looks like this. That is a carbon dioxide halo, coma around 3I Atlas that's off-gassing a tremendous amount of carbon dioxide. And that was the first real SphereX discovery. That paper, that was our first in-house paper. We went from data to paper in 10 days, which is a record for me by like an order of magnitude. Pretty amazing, but when you build an instrument like this that's so new, and that data, it just falls right out there. It makes the analysis easy compared to the other stuff that we're trying to do for cosmology. It's going to take us years to get to a single number we're extracting. This just falls out. And what you can see there, so this is what a spectrum looks like from SphereX. And we've also got an image for each of those, each color that's around a region of the spectrum corresponds to the image. So you can see at 1.5 microns, it looks like a little dot. At 1.5 microns and stacking up there, that's the dust and the core that's reflected sunlight. Right, like you would look at it in the optical, you see that reflected sunlight, and it just looks like a dot. But of course, in CO2, you can see just how extended that is. That's around 4.3 microns. Importantly, around 3 microns, you see nothing, and that's a telltale signal, as we know, of water ice. So this was huge. The other thing that we didn't see, of course, is out at 4.7 microns, which is where CO, carbon monoxide, lives. We did not see anything there, so we published this paper, just strong evidence for water ice and this extended carbon dioxide. About 3 days later, after we put this out, the NIRSpec team from James Webb's Space Telescope put out this spectrum, which confirms our findings. And they, of course, have a huge light bucket with an amazing spectrometer, and you can see that in great detail. They see the water ice, they see that carbon dioxide. And they actually do detect carbon monoxide. They're more sensitive, but at a much fainter level. So if we look at the comparison, though, you say, okay, this is a beautiful spectrum with James Webb. What do you need SphereX for? Well, let's compare these 2 images, right? You'll see this made its way out there. You see the James Webb carbon dioxide image and the SphereX carbon dioxide image. But when you put them side by side, you're missing a very important scale here, right? That's the 2 together. Okay, James, if you zoom in there, that's what James Webb sees, right? So it's an amazing complementarity, right? They're this big, huge light bucket that can go super deep, get great signal to noise, but they miss the huge picture, right? And we could see that extending to 0.1 degrees, right? That's hundreds of thousands of kilometers in radius going out at 3I Atlas. This was also a big deal for me because it was the first time an image that I had produced came up in my newsfeed doom scrolling. This is the internet having their way with Minneapolis. Is Earth under threat? These photos serve alien attack buzz. But I was also happy to see that it shows up in things like this. No, our solar system's interstellar visitor is not aliens. Here's the science to prove it. So the internet has really taken off. There's been some vocal proponents. We should be open to detections of intelligent life. Absolutely, it's out there and we should be there. This is not it. I mean, it would be a remarkable, it looks so much like a comet, but it is not exactly like a comet. It has an incredibly different ratio of carbon dioxide to carbon monoxide. It is water poor. This is a fantastic, wonderful thing to think about in its own right. We don't need to call it an alien spaceship to make that interesting, in my opinion. So we saw it back in August as it was moving towards the sun. Then it goes away where you can't see it. That's kind of, it went away September. And then just a few weeks ago, October 29th, it passed closest to the sun. We couldn't see it at this point, but when a comet passes close to the sun, that's when it starts getting interesting and lighting up. Right now, earthbound telescopes are hard to find because it lives in daytime, it lives right by the sun. But it's moving, and in mid-December, in a couple of weeks, it's going to come back into our field where we can observe it again, and hopefully we'll put on a good show for us. We could see some really interesting extended stuff. We might be able to see that it's carbon monoxide as the core starts to break up. Water is going to evaporate now, so we can start to see water gas, things like that. Who knows? Who knows what it's going to put on, but it's super fun because it's a real-time experiment. We're cosmologists, we're not used to things changing, on real-time scales. But now it's super fun to study this object. And the data is out there. It is open to the public. Here's a website. I encourage you, the Santa Barbara Astronomical Unit, any object you're looking at, go to this website. You can enter in whatever coordinates, and of course we've done the whole sky, where it's not quite all the way up there yet, but will be in a few weeks. Wherever you point it, you can get your data and put a SphereX spectrum on whatever you're imaging.
Sorry, what's the website?
Oh, this is at ursa.caltech.edu. You can see it up there. But if you just Google SphereX Ursa, IRSA, you'll be able to find it. And then it has you can search and find whatever coordinates, and you'll get spectral images that are like this. So I encourage you. We have good data that we know that the data set that we put up there has been downloaded over 10 times over. So people are downloading that, and we're very excited to see what comes out of the community. We've had a few papers that just come out of the community already, and it's only been up for a few months. So at this point, I want to kind of take a higher view. The SphereX was such an amazing effort from so many people, great scientists, great engineers, managers, administrators, all sorts of people, and it's really amazing to get to this point. I'll call out a few people who happen to be with us tonight. Here's Howard Hui and Cheen Wan. These are my core instrument cronies here. They did all the spectral calibration and put the thing together, and we're still operating SphereX together. You're going to get to hear from Howard in a few months on some other work. And Ari Zuckerman, who is leading the EBL team and had done so much of those mosaics, those all-sky mosaics and the deep mosaics. So it's great to have him with us tonight. And it's so fun coming up here, and I hope I conveyed some of my excitement for SphereX to you. And this is a great community that you guys have up here, and thanks so much for having me.
I'm a little confused about all of this, but I am interested in the fact that you were saying something about the universe is a flat plane, and you were talking about the web of
That's right.
objects that are, can you just give us a little bit of
Well, it's spatially flat.
Try to repeat the
Okay,
question.
so the question was about the spatial curvature of the universe and what it means to have a flat geometry. It's a great question. And when we say flat geometry, it's not all in a plane. This is in the general relativistic sense of curvature. So as Einstein showed in general relativity, space-time can be curved by gravity, right? So when you have a massive object like the sun, it curves gravity, and the motion of planets around it can be caused from that. When we say spatially flat, on the largest scales, that is not true. There's not some big warp that goes across the entire universe in this gravitational field. It's remarkably uniform on the large scales. It has these dips in curvature where there are massive objects that live in it, but on the largest scales, it's uniform, which implies that the very earliest epochs of the universe, everything that was in thermal equilibrium, and that's why we get to inflation, because it blows things up and smooths everything out. It doesn't have these big wobbles that go across. So you need some mechanism like inflation to flatten everything out.
And then this web.
The cosmic web, that comes out from the perturbations. Those are the little overdensities and underdensities. The little wedge, but the little wiggles on the large scale. And that's where galaxies form. They're not random. Galaxies don't look like, just completely randomly oriented. They're clustered together. There's a structure. And the information that's embedded in that structure tells us a lot about the universe.
And you said that came from the quantum, what was going on at the quantum level?
That's right. That's right. It's seated at quantum fluctuation. So we can observe this in laboratories on quantum scales. That's where the uncertainty principle and little perturbations that are sourced in quantum mechanics. So this really is a beautiful measurement because it ties the physics of the smallest scale to the physics of the largest scale.
What
Yeah.
is the anticipated lifestyle of SphereX?
Yeah, so then the question was about the anticipated lifespan of SphereX. So our baseline mission is 2 years that have started from May 1st for data collection. We call that phase E. That's what we're in right now. And then there's a further year that once we have a complete 4 sets of all sky spectra to analyze the data and get to our final cosmology results. SphereX can be extended. It's a question of support and whether or not the funding powers choose to extend SphereX. Yeah.
What's the shortest wavelength in the visible that you guys are imaging?
It's not quite visible. It's 750 nanometers, so it's just kind of at the edge of what visible is. It's very bright.
And what's the resolution in arc seconds per pixel of it?
6.15 arc seconds is the resolution.
On the comet, has anybody backtracked the trajectory and tried to find an origin point? I mean, we know they're not aliens, but...
Well, yeah, and maybe you've read something online about that. But so yes, that has been backtracked back. There's a physicist at Harvard called Avi Loeb who is a big proponent of this kind of technological signatures. And he claims that it's coincident with the WOW signal from the late 70s.
Oh.
At a 9-degree uncertainty. I'm not going to put a lot of, he went through that. But the problem is that if you're trying to find a home system, that it's everything, you don't know the trajectory that it came out of, right? It gets kicked by a giant planet, coming around and gets a kick, and you have no idea what the impact parameter of that is. So you don't know, how that comes around. And then it's been traveling for 1 billion years or so.
Okay.
The galaxy has been orbiting around, so it's really hard. But that is so one clue to that could be the ratio of CO2 to CO that we measured, and that could be one of two things. It could be an indicator of a home solar system that's very different than ours in their ratio of CO2 to CO, or that could be a product. There's another paper citing that's the consequence of being exposed to galactic cosmic rays for 1 billion years or so. And you can convert in the laboratory under this radiation from CO to CO2. So we don't know. So it's very interesting to try and find a home system. Yeah.
And New Horizons is trying to do some of this background light stuff. Does that jive with what you're seeing?
That's right. Well, the question was about the New Horizons extragalactic background measurement. So what they do for New Horizons is related, but not exactly the same measurement to what we're talking about. So we study the extragalactic background light, same signal, but we do it through this intensity mapping technique, right? We're studying the wiggles in this field spatially. What New Horizons is doing is to measure the absolute intensity of it. That's a very important measurement too. That's weighing, you know, the pool of light that has come out there. That's really hard to do from our house at 1 AU from the sun because we're embedded in the zodiacal dust cloud, right? So we have a tremendous foreground that is, you know, order of magnitude brighter than the extragalactic background. New Horizons went out to Pluto. So they got, it's the only foreground in astrophysics that you have any shot at getting actually past is the zodiacal light. You're not getting out of the galaxy, right? We have to deal with foregrounds in the galaxy. No spacecraft we build is going to get out of the galaxy. But you can do that, and that's what New Horizons does. And they're only measuring, New Horizons has a broadband photometer in the optical, so they get 1 point. Right? And we have 100 points in the near infrared to go after, but not the same exact measurement.
What are the various other molecules that you're looking at besides water, carbon dioxide, carbon monoxide, methane?
Yeah, those are a lot of the, you know, the classic hits there. But, you know, there's tons of lines in the near infrared. Lots of hydrogen series from H2 regions, you know, bracket alpha, the Fund alpha, Fund beta, all those different series of recombination lines. PAH is a big one for us, which is polycyclic aromatic hydrocarbons. Those are, you know, you see that in diesel fumes and barbecue, whatever, that kind of stuff, and it's really interesting because it's so organic, big organic hexane.
Buckyballs. Huh?
Yeah, well, not quite buckyballs, but yeah, it's similar, big hexanes, hexane things, and there's all sorts of. We keep finding new ones. We find lines, and we're like, what is that? And you have to go look it up in an atomic line database. Yeah.
How many colors did you say? Was it 20 or 40?
It's 102.
Wow.
So it's 102, although this is how we discretize. It's 102 resolution elements. But those linear variable filters, it's not discrete. It's not like band 1, band 2. It progresses in wavelength. So the real answer is 24 million different band passes, right? When we did that spectral calibration in the lab, we had to measure 24 million band passes, not 102, right? Because each pixel has its own band pass.
I have a question.
Yeah.
It's in a polar orbit,
Mm-hmm.
and it means it had to be launched from Vandenberg. They can't go a polar travel, can they? And it's always looking away from the sun.
That's right.
It can't possibly, as the Earth turns, it can't possibly go down one specific longitude. How many in a day? Let's see, an hour and a half,
Yeah.
does it go
It's
over
about
1.5?
It's like 16 orbits a day. Yeah.
16 orbits a day.
Yeah.
But the only way it's gonna take in the whole universe, since it's gonna be on the same track, is
Yeah.
the revolution around the sun.
That's exactly right.
No, okay.
That's exactly right. That's why it takes us 6 months to complete a survey.
So we gotta, okay, 6 months.
It takes us 6 months because you're observing on both sides,
Okay.
right? So you get 2 in either. But they're actually different. The first 6 months, because of the parallactic angle, the way that our focal plane goes on our first survey, you could think of like pointing up like this. We'll look at the sky looking this way, and then on this side of the Earth we look this way, right? And then the next 6 months when we come around, we look at that same part of the sky going down, so it's flipped over every 6 months. But we can make a full map of the sky every 6 months, and our baseline is to do that 4 times in 2 years, and we hope to extend that further.
You kicked it off right after the March 11th launch. It was.
That's right. We commissioned it first. We took a month to commission it and turn everything on very systematically and run a handful of tests that we can't get from our survey data. And we started our survey May 1st.
But is it instant flashes of pictures, or is it a moving video?
Well, each picture takes us 116 seconds to collect. So we stare at a part of sky for 116 seconds.
2 minutes.
We process that on board to turn that into an image. We do what's called sample at the ramp, where we measure how many electrons per second are liberated from staring at an object, and that's what's sent down to Earth. And then after that 116 seconds, we make a little small maneuver, and we look at a different point, and then we do another 116 seconds, ad nauseum, forever.
Are you transmitting the data back like in a stream all the time, or packets? Or
Great question. So this is a question about how we get our data down. We use what's called the Near Space Network. So we have 4 dishes that we use across the Earth. We have one in Punta Arenas at the tip of South America. We have one at Svalbard, which is north of Norway. And then Fairbanks in Alaska, and Troll, which is in Antarctica. Not a coincidence that we do this all at the polar regions, and if you think about our orbit, that's because we can see them more. So we do that in about 5-minute chunks when we go over the ground stations. We have antennae on the bottom, and then we point those at the ground. We take time out of our survey, we point our antenna to the ground, track that ground station, dump our data down, and then continue on our merry way.
Yeah, kind of, also, just, I don't know how you did that with the budget that you had. It seems like such an incredible mission, so rich, and all the people involved. I mean, man,
Thank
you
you,
guys
yeah.
are worth $1 billion, right? You should have $1 billion.
He was going, but yeah, it was, we like SphereX, we like to think of as a good bang for your buck. You get a whole lot of science, and of course, we designed it to do our 3 core science themes, but anyone can go mining for whatever information you want, so the data's out there.
Are you able?
So the budget was $350 million.
So congratulations on the foresight 13 years ago that you had this interstellar visitor.
Yeah.
But as planets come through your field of view, do you saturate the detector, or can you actually get?
Yeah, the question was about imaging planets, and it is a difficult, actually, question to answer. It's a whole mixed bag of stuff. The large planets, remember, we're never looking in, so you'll never get Venus or Mercury. Looking out, and we've seen Jupiter and Saturn, and it depends on what wavelength you're looking at, right? Jupiter has tremendous methane absorption, right? So on the methane line, where it throws away 4 orders of magnitude of signal, we can image it because it's taken out. On the peak of the emission, it's completely saturated for us. We can see the moons though. We can look at interesting stuff. It just becomes very difficult around bright sources. And they're not point sources for us. They're not very big for us. They're, Jupiter I think can be like 20 something arc seconds. And so it's resolved, but it's not that resolved, and it saturates a lot of pixels, and it's getting new science is really hard on the big planets because they're just so bright. And we built this thing to look at really faint signals. Yeah, in front.
What's the best way that we can support you or your project, what you're doing, whether that's like word of mouth or otherwise?
Oh, thanks. Yeah, the question was just about how we could support SphereX. And I just think getting the word out, making sure, the association with SphereX is awesomeness. And, that's what we try. We certainly believe that. And, we're, times are interesting right now for funding in science. We are fortunate to be most likely funded at least for our baseline mission. But, we're coming up for a senior review, and we think we could extend this mission and continue to get great stuff. So I would just say, use the data, write papers. That's the way you use it. Use our data and discover stuff. Yeah.
That actually reminds me then of a question as a college teacher. Do you have an education element to your project? Are you looking at that?
Yeah, well, we have even there's some undergrads at Caltech, for instance, that are working on, we have research summer things. I don't know, we don't have a sort of citizen science thing, but I would certainly encourage people such as yourself, our data's out there, right? Interesting spectra, that'd be a great class assignment, extract a spectrum of M82, or, things like that, where you kind of know the right answer, and you can actually do data analysis workshops, and you could learn new stuff too. The data is out there. There's no way we're skimming all the information. It's just out there, and I would absolutely encourage. There's great student projects that can be cooked up with our data. Yeah, with that.
Since you're not worried about cryogenics running out, what would be the limiting factor that might end the mission?
Another great question. The question was about what would limit the lifetime. So, we rely, you're right, there's no cryogenics, no consumables, there's no thrusters either. There's nothing that we consume on board. The limiting factor is actually the drift and the precession of our orbit. The ML10 of our orbit. We use ML10, mean local time of the ascending node. So we're locked in that polar orbit, and it's important for us to be that way because we can't let sunlight in, and we can't let the Earth shine in. And as the time goes on, we get dragged from the solar wind, right? It decays our orbit and pushes us down. The orbit will precess. We can't maintain that. So eventually, it'll start to drift, and then there will probably be times where we can't point anywhere safe. We'll need to warm up. But ultimately, we've got 25 years because at that point, the orbit will decay and will burn up into the atmosphere. And that's a requirement. That was a requirement that we had to burn up in the atmosphere within 25 years. So we designed the orbit specifically to do that. Yeah.
How do you point your antennas? I would imagine it's not mechanical. Is it like a phased array? And then what's your power supply?
Yeah, okay, so the power supply is easy. It's just our solar panels on our back. So it's all solar. And it's not a phased array. They're two medium gain antennas to talk. And everything is done inertially by pointing the whole spacecraft. Right? We've got a series of reaction wheels on board, gyros, that are spinning, that can point us any which way. We also have what's called magnetorquers, which dump angular momentum using the magnetic field of the Earth.
And those 3 cups you saw, those
Yeah.
look like tin cups or
Yeah.
Dixie cups.
Photon jets.
They're only for cooling, they have nothing to do with channeling light wave, right?
Well, they're for cooling, but for blocking out the sunshine also and the Earth's shine. Remember, Earth is glowing below us, so it's a shield. It's not a collecting device. It has 2 jobs: to block sunlight and to radiate out our light.
Well, Dr. Phil, can you conjure up those words again that gave us the acronym SphereX?
That's right, okay. The SphereX acronym is the spectrophotometer for the history of the universe, epic of reionization, and ICE's explorer. Thank you so much.
Can you and Dave Grossman give as good a speech as this next month? We're going to be here anyway. Fascinating. I have to give you a couple of gifts here. This is our club's tote bag. And inside is something designed by the original Chumash Astronomy Club hundreds of years ago. Your honorarium is inside there, Doc.
Awesome.
And are you spending the night in our town?
In Buellton.
Oh, in Buellton. And the gang is going home, or are you going to party in our city?
Around.
Ojai, Ventura,
August 7th, Dr. Wee, you want to raise your hand? And you're connected to me. He's what?
Caltech is
Well, I know that, but you're connected to the South Pole somehow. Can I just tell them that? All right, and this is your incredible tote bag, and I think it was great. It's one of our best. You'll be on if you'll hold on a second by the president, and invite you to come back next month and vote if you're a member. If you're not a member, become a member and then you get to vote. There's 4 people we're voting for, and we'll have these 2 gentlemen speaking. We'll see you tomorrow night at dark next to the observatory, everybody, for a star party. Thank you for coming. We can make a little, can't we? Mr. President, you want to close the meeting?
This meeting is adjourned.
Looking for a person. Sorry. Let me know when you're. Tessa, where's Duff? Duff.
so you're broadcasting in,
Whatever you do is nurture